Swayam Prabha. Digital India. Educated India.
So, this is kind of the work that really did set up this field of streaming. There were streaming algorithms which were kind of precursor to this, and like someone was talking of, I did discuss a variant of Lajolet-Martin, Mr. Grice. These are streaming algorithms. Morris's approximate counter, these are streaming algorithms, but when they were described or papers written, the people did not talk too much in terms of streaming, but this paper actually did set up the theoretical basis of it. So, it was a paper in a journal called JCSS. It was a paper in the mid 90s of the earlier century, 1995 if I remember correctly, and this was a Gödel Prize winner. The power of the algorithm is like, what I would do for you is I define the problem for you and kind of not discuss it in its entirety, but just look at one particular frequency moment and point you out maybe connections to other areas. Well, so this is known as the AMS, popularly in the community this is known as the AMS tug of war sketch. There is a term, meaning of this term, maybe I will just talk of this a little bit. So, A stands for Noga Alon, M is for Matthias and S is for Szegedy. So, Alon, Matthias, Szegedy. Before I get into the problem, let me talk a little bit on sketching. Sketching is something like this. Say, so I was setting everything around this network router problem, right. So, say for example, you had this network routing, this small computing device on the network router computing something for you today. So, there was a stream sigma 1 for today, right, and say you have computed some function over this stream, something. Now, the network router traffic has to do its job now again on the next day. So, there is again a stream sigma 2. So on and so forth. Now, your life is such that you cannot store anything or store almost very negligible quantity. Now, say for example, you want that I want the same thing over these 2 days. So, that means your new stream is and you want to compute you understand, for some functions it is quite easy, like if you just want the average, not a big deal, but there can be many functions for which it is not easy. So, the question is, can you get f sigma in terms of, so if you can do that, then it is very good for me, right. So, what I can do is today's f sigma 1 I compute and keep it. Tomorrow also I compute a new f sigma 2, and then I can out of f sigma 1 and f sigma 2 I can do something, say maybe compute another function to get my f sigma. If I can do that, then this is known as sketching, linear sketch, and not all streaming problems do admit linear sketching. frequency moments does. So there is actually again a literature, if you look into the streaming field, there is this field of linear sketches. So anyway, just I wanted to tell this term to you. Now let us get going on frequency moments. Okay. Yeah. So the setting is same. I have a stream of length m. Each AI belongs to the same setting. Now the stream implicitly defines a frequency vector. So there can be n elements, right? Each one appears in this stream with a certain frequency. So this is the frequency vector. Let us call that to be some f. So what is Fi? Fi is the frequency of AI. What is summation of Fi? What is summation of Fi? Length of the stream, right? So it is m. So the kth frequency moment is defined in the following way. So you look at the ith element's frequency, raise it to the power of k. For our case, k is an integer, but even it works for real case for certain ranges of k's, but for our case k is a positive integer, fine. Okay. And then I sum over all. It's like that. This is the frequency, you are looking at the kth norm to the power of k. So what is F1? F1 is just this one. Okay. What is F0? N. Why it should be N? Now 0 to the power of 0, why should I bother about frequencies which are 0? Look at this sum, right? For elements which has a positive frequency, you are putting index power is 0. So for each, the presence of each distinct element, you are adding a 1. So you are basically looking at the number of distinct elements. Good. So you straight away understand this is an important thing. and I had tried to convince you that frequency moments has other uses in figuring out distributions and stuff. So, this turns out to be a very useful thing to compute. Again, there is an impossibility result which tells you that if you have to exactly compute this fk, so the algorithm that we would study is actually this for k equals to 2. Right. So, we will be interested in f2. So, that means I am looking at hey, why did I put k up there? This is n. Fine. Think of finding this sum. So, you have a stream, elements in the universe coming. So, you get one element. First of all, if you have to figure out its frequency, then that means if you have to go this way, then you have to get the frequency of each and every element, then raise them to the power of something. Now, if your f0 is high, that means if your number of distinct elements is quite high, then you have to store those many counters to figure out how many distinct elements are there. You might even argue that some of the distinct elements might have a lesser contribution in terms of the frequency. So, why do I bother about them? Because first of all, notice this, that the quantity that I am trying to find is kind of a sum. It is aggregating. You are supposed to return a sum of some square numbers. So, it may be the case that I do not need to store everything. Now, what often comes to your head is I have to store everything, count its frequency and then add. But the ultimate quantity that I am to compute is just a number, right? So, what I can do is I can look into the fact so say this ith element comes, ai comes, I add up 1 to the sum, aj comes, I add up 1 to the sum, I keep doing it. But the catch is I have to in some way figure out the frequency of ai, right? So, what I tried to do was I tried to first convince you what is kind of the difficulty of the problem, and then possibly indicated to you that there is possibly a way out to get around this difficulty. Well, the streaming world is such that whenever you are in difficulty, hash, right? Okay. But how do I hash? That is how do I hash, what kind of hash that I use is a thing to be decided, right. Now, the moment I give you the algorithm, you would just be shocked at how is this going to really compute what it is supposed to compute. So, my initialization step is, as Venkatesh and Devoshi has already told you, that how you can design good hash functions, good meaning good for the present context, and the amount of independence that you require out of this hash function. So, choose a random hash function And by now this term should be very clear to you what choosing a random hash function means. I will give you this range of the hash function a little later from a, this also will come later. We will figure out what kind of independence we need. So, also by now you know that the degree of independence that you require out of the hash family dictates the space that you need. Fine? Okay. So, your first initialization step is, so this x will actually count the frequency. I set it to 0. These are my two initializations things that I have to do for this step. What you do is, the moment you get value in the stream, sorry, you get a token from the string j which is in the universe, just like the morning. Just this does it. A suitable hash function, but this hash function is still not very clear to you, right? I am kind of making it hazy for you, but what I am telling you is, I look at this value, x is the counter which is kind of storing the frequency moment value, and I am getting a stream. What I am doing is, I am passing it through a hash function of certain range which is not yet fixed for us. We will fix this soon, and requiring certain amount of independence. And even I would give you the output. What should I output? So, the algorithm has finished. Stream comes, I had set this counter x to 0, stream comes, I hash this j, add it to that whatever is there in the x counter. Once the stream finish, I will give you something. What should I give you? So, I should give you something which is a function of what is stored in the counter, right? So, in the counter it x is stored, right, suitably modified with this hash function value hj. But what is the function that I should return for you? Mind you, I am looking at second moments. X was just the sum. So, what should I return? Can you make a wild guess? Good. I heard it. Good. Just return x square. Now, after at least something is clear and some parts are hazy, can you tell me what should be this range? What should n map to? Elements in the universe map to? Think of the morning thing, the last thing I discussed in the morning. Come again, someone said something. +1 -1, okay. What made you say so? Yes, there is a square term there. Good. You see, these people are all attending tutorials. No, you answered without attending the tutorial, right? That's great. Yeah, that's it. We will fix this independence a bit later. So, it is such a difficult problem, and that is just you see the line of codes. Done. So, what I have to prove is that this x square that you return is an unbiased estimator of the second F2. So, if you think it in terms of sketch, so the sketch that you store is not x square, but x. So, say for example, this network company wants to find the F2 for the data that went past on the first day and second day. So, what it would not do is it would not store x square, it would store x for the first day, x for the second day. Then look at the sum and square. But one thing you should keep in mind for this to work, the hash function used on both this should be the same hash function, else this is not going to work, right. So, you can make a note of this, that if you want to turn this algorithm to a sketching algorithm, you better use the same hash function on for the separate streams. Anyway, so now let us get into the analysis, but you can understand what is the space, right. Space is what? You can count only up to m. So, space is log m, right. So, just need of a counter. Okay. So, space is need of a counter plus this hash function storage. So, hash function storage is nothing but storing this, by now you know coefficients of those polynomials, and they come from a certain range. Okay. So, the hash function storage, this will be fixed when I fix the, what is the amount of independence that you need. Good. Okay. Now for the analysis. I denote yi as a random variable denoting the hash function value for each I in n. What I need to prove, required to prove is for unbiased estimator, expectation of what you returned. So, though you stored x, but you returned x square. So, this is equals to F2. So, just hold on, what was x? So, x was this x plus h, right. So, that contribution was coming from, so everything was coming from this y, right. Okay. So, maybe I can make a note of this, that x is nothing but summation fi yi, I equals to 1 to n. Because x was kind of absorbing all this thing, right, all this yi is the hash function. Just so this actually comes from the code, right. So, this is actually the hash, this yi values, right, they keep on adding, just they keep on adding, piling up one after the other. But again the saving grace is this plus minus 1. Fine. So, the problem now is, till now you had handled only power of 1 for random variables, right. Now there is a excess square term. So, that means you are now looking at, the moment you are looking at excess square, then it is a sum and you are taking square of that. So, there would be individual terms as well as product terms, and you know by now handling product terms in probability is really the challenge, and you really need independence to tackle that. Independence is the hammer with which you kind of thrash it, and that is the reason I set my HIs to be independent. Okay. So, this is expectation of, now I just use this, I think I should erase this one, yeah. Done, right. So, you have this product terms and the sum. Now, this yi's take value plus minus 1. So, yi square is 1. So, the first term is nothing but what I wanted, good. So, I just apply linearity of expectations, where this term comes here, this term gets here, and this is f2 plus. Now, notice one thing, fi's and fj's, as per the argument in the morning, they are constant for this random process, because the frequency of an element is what it is, there is no randomness to it, right. So, these are constants for me, agreed? Okay. So, I can look at this sum as ij fij into expectation of yi yj. Okay. So, what is the source of randomness for this yi's and yj's? It is coming from the hash function. So, now if I want to write this, as, mind you, I have not yet given any independence power to my hash functions, but if I kind of want to write this as this quantity as this quantity, then what is the independence power I should give to my hash function? 2, right? Right. So, you have really understood this k-wise independence. So, I give this, so at least for now I make it 2. We will see what we need for variance. So, if it is 2, I am happy that this calculation for unbiased estimator is going through. Then this term gets to 0, I am done. So, this is an unbiased estimator. Now, pause for a little while and think really why did it work. Think of it. What I was trying to find out was, so it was like frequencies of different quantities of the distinct elements, each one raised to the power of 2 and its sum. I agree that this is an aggregating quantity, like if I look into F1, it's nice, right? It's just a linear sum, things work perfectly well, but this was a quadratic sum of quadratics, right, raised to the power of 2. Now, why really did this simple algorithm work? The answer lies in returning this x square. So, what you did was, see, x is just the value that the counter is storing. Now, when an element comes, it is going to add, so if say for example, j is one of the elements in your string. So, this is being mapped either to +1 or -1, but if again j is going to come, it is again going to come, if it came with +1 earlier, next also it would come with +1, but another j1 which comes with -1 will again come with -1. So, this is this tug of war going around, and finally this x square actually lifts everything up. Now, if you really knew something called Johnson-Lindström's lemma, then I could have even given a better explanation of why this really works. But I think Johnson-Lindström is there in the later part, but again then I will not be there. Okay. So, two things to be done, one after which one we have done. It's like we have proved that Alon Matthias Zegedi's algorithm returns an unbiased estimator. So, next is controlling the variance, so that tail inequalities behave nicely. Okay. Now, see, for variance you are looking at square things, already it is x square. So, variance will lift it again to another square. So, now you have to handle terms which have power of 4, and life would not be that easy now. Okay. So, let us get into the variance estimator. So, I am interested in variance of x square, which is e to the power of now x to the 4 minus e to the power of x square whole square. So, e to the power of x square you have already computed, right? E to the power of x square was, expectation of x square was f2. So, this is expectation of x4 minus f2 square. We have to figure this out. This is not a very nice term to handle, but let us see. Let us write this out. Okay. So, if you, so this is kind of terms like a1 plus a2 plus dot 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 to the power of 4. So, there would be fourth power sums and the rest. So, powers of like 1, 3, 2, 2, so on and so forth, right. Okay. So, let us do that. Kind of I subsume everything by writing it as follows. And I look at right. Mind you, I am using this x to the power of 4 is this sum raised to the power of 4. Agreed? So, fun things will happen to this nasty quantity if you give suitable independence power. Again, see, where is the source of randomness? Here, right. So, if you give suitable independence power to your hash functions, probably these quantities can also be managed. Okay. Let us now focus on this. Look into this fourth tuple. And say look at a term like this without loss of generality, that I does not belong to j, k or l. So, that means I is the term that appears exactly once in this fourth tuple. Now, I want to write as this. I want to write this. When can I write this? So, if I have a 4-way independence. See, if you had 2-way independence, you could write expectation of x and y to be expectation x into expectation y. So, if you have 4 ways independence, you can write this. And now this will do magic for you, because what is expectation of yi? Yi comes from a hash function hi from n to plus minus 1. So, in the morning we have done this. What is this expectation? So, someone said no. Oh, it was a nod of acceptance. I thought otherwise. No one wants to be challenged, you see. Fine. So, in the morning also we have seen, right, this. So, that means this 4-way terms, if you give enough power to your hash function, some of these bad terms get away. What remains are the pairwise terms and the 4th order terms. And this would, as I would show you, would be easy to handle, because the moment you look at a square term of yi square, what is that? Always plus 1, right? Because you are hashing to plus minus 1. So, that is a expectation of a constant, it would go away. Okay. So, this discussion implies the following. So, the terms of importance are the ones having, how do I frame it? fourth power or 2 squares, maybe that's the way to put it. So terms like x to the power of 4 or xi square xj square, or rather terms I should say in terms of y. So either the term should be like yi to the power of 4 or yi square yj square. Now let us come back to that expression. Now we just go through the motions. These are the fourth order terms. Now there would be second order terms. How many such terms should be there? So this is a term like II, JJ, right? So if you fix I and J, then you are done. So you have a fourth tuple I, J, K, L, of which if you can fix I and J, these are this I square and J square terms. So there would be 4 choose too many such terms, right? The set is I, J, K, L, and I argued that either the if you expand this product, I can forget about this 1 3 and 3 1 terms. Remaining is the fourth powers or I square J square, right? So that means the way you can choose 2 out of 4. So this is like 4 choose 2, 6. So now your life is easy. Yi to the 4 is, each yi is hi, right? It is either plus 1 or minus 1. So the first thing computes F4 for you. The next is 6. Why does this term go away? But again, because that's a constant, right? So expectation of a constant is a constant. So I have now got rid of all expectations from the expression. It is now just simple algebra. What kind of algebra do I use here? This simple formula of x plus y whole square should be equals to x square plus y square plus 2xy, right? So you can write xy in terms of the sum of squares minus the squares. So do that. So use the fact that xi plus xj square is equals to this implying thereby that xi xj is equals to half So coming back, what I have is variance of x square is now, I got that f4 term, there was an f2 square term from the beginning, and then I had this 6 ij this terms. this is equals to f4 minus f2 square plus 3, 3 because you get a half here. This is f4 minus f2 square plus 3. This is nothing but f2 square minus f4. So this is equals to twice f2 square minus twice f4, which is less than equals to twice f2 square. Mind you, Chebyshev works if I can just have an upper bound on the variance. So you need not really write down these calculations, right? These slides would anyway go to you. So, okay, now use Chebyshev. What I returned was x square, f2 was what I wanted, less greater than equals to epsilon into f2. This I know by Chebyshev's formula is variance of x square by epsilon square this, and so this computes to 2 by epsilon square. So I have got a control on the variance in terms of the epsilon, the error parameter that was set by the user. Now this is exactly in the Morris setting, right? So I can apply this median of means improvement using Chernoff and to get a final epsilon delta algorithm. So this is your exercise. Use this medians of mean technique to generate an epsilon delta algorithm. Okay. So what was the independence level that I needed to write this? Was 4y's, right? So let us go back and fix it. So now I know everything should come from a so when I write 4y's hash family, it means 4-way independence of the hash family, right? Maybe I can just scribble in the word independence here. So do you have any questions? So if you now think of this this median of means applied to this problem. So think of this in the following way. So you had a frequency vector, right? So your stream was nothing but an implicit n-dimensional vector. Now you first allow it to go through this basic unit of AMS algorithm, giving you this 2 by epsilon square error bound. So then what does this median of means technique does? There are multiple copies, you aggregate some of them, get an unbiased, so it's like sum of IID random variables, right? Then you have t many copies of them, then you take the median. So you can look at it in the following way, that this vector, which is kind of an n-dimensional vector, you have transformed it into a t t-dimensional vector, right? So you remember this Morris's, from there you generated this Morris plus, of which you took there were t many values from which you took the median. So I am stopping at this level just before taking the median. So that is a t-dimensional vector, there are t values in there from which you are taking the median. So this is kind of a dimensionality reduction. And your Johnson-Lindström lemma tells you that if you are interested in the second norm, L2 norm, that means the one which you know as popularly known as Euclidean distance. If you are interested in that, this median of means technique actually preserves this L2 distance within a 1 plus minus epsilon error. And that is the reason this median of means technique is working nicely to give you a nice estimate of F2. But without a knowledge of Johnson-Lindström, this would be difficult for you to understand. But what I have done is I have given you a very, what should I say, a hand waving idea. So once you read Johnson-Lindström in the next week's lecture, think over this, right? What I am supposed to do was, I was supposed to figure out this, right? This is what I wanted to figure out. So this dimensionality reduction actually preserves the squared distances with some error. And that is the reason, just by looking at the small vector, things work. I think I will stop here. Okay, so enough of lectures. Today was my last, but yours don't end. You have to be here for